Revision Topic 01, Numbering Systems. The human body has a very strong reliance on electrical signals. Everything we see, look, touch, smell is translated in one form or another into electrical signals. So our entire interaction with the real world takes place via electrical signals. And then, of course, these electrical signals are interpreted by our brain. When it comes to the human inputs, we have the human ear, which is responsible for taking the audio signals that we hear and translating them into an electrical series of impulses that can then be interpreted by the human brain. We have the nose, whose responsibility it is to translate our smells and our tastes into electrical signals. So all the nice smelling roses and flowers that we smell of a day are simply translated to electrical impulses by the nose. When we enjoy a wonderful meal, it is the nose's responsibility to translate that into electrical impulses for us. When it comes to sight, it is the human eye that does a very complex transformation of things we see into a stream of electrical impulses. This stream of electrical impulses is then interpreted in some shape or form by the human brain, which allows us to, see what we see. The sense of touch, this is our entire body is covered with nerves on our skin, that when we touch something, whether it be hot or cold, or rough or smooth, or fluffy or nice, it is these nerves on our skin that translate that sensation into a series of electrical impulses that then allow us to interpret it by the human brain. So all of our input from our outside world is in fact translated by these various components into a series of electrical impulses. When it comes to the output, that happens in exactly the same way. It is a series of electrical impulses that are then translated in some form to produce the output that we produce from our human body. So one of the most common forms of output is, of course, movement. So we get a series of electrical pulses from the human brain with perfect timing that then triggers our muscles at the precise moment to allow us to walk, or to move our hands, or to play sports. It is the muscles that are interpreting or translating this electrical impulses into movement. We also have quite a complex vocal system, which is half of the communication system that we're using, which is primarily the mechanism I'm using now to try and convey this information to you. It is the speech system. So using a series of electrical impulses, the human body is able to modify the diaphragm, modify our larynx, cause our vocal cords to vibrate, allow us to modify the vocal cavities of our throat and our mouth and our nose, that allows us to make the speech that we can then interpret. So it is these electrical impulses that enable us to make coherent speech. Okay, so the numbers are extremely important to computers, and they're also important to us. We like numbers because it gives meaning to our lives. It allows us to quantify things. It allows us to, work out exactly how much money we have in the bank. It is the numbers that tell us our bank balance. It's the numbers that tell us whether we can or can't go to the movies this week. It is the numbers that tell us how old we are. It is the numbers that tell us whether we've passed or failed a subject. Numbers are extremely important to us, but they're ever so more important to computers. Because even though computers are made up of electrical signals, it is the information transferred in these electrical signals, hence numbers, that is extremely important to computers. Computers rely heavily on numbers. All of their inputs are numbers. All of their outputs are numbers. A microprocessor is nothing more than a calculator. It simply takes numbers as an input, modifies them in some way, and gives another number as an output. So numbers are extremely important to microprocessors. So when it comes to microprocessors or programmers, who are the people that are programming the microprocessors, there are a series of number systems that are extremely important. These numbering systems are the binary numbering system, the octal numbering system, the hexadecimal numbering system, and of course the binary coded decimal numbering system. Of course, there has to be some way for us to easily represent a decimal number using the native binary number of computers. Okay, so when it comes to counting, there are 3 rules for counting, whether you realised it or not. But when you learnt to count in primary school, those teachers were effectively teaching you these 3 rules. So by making you aware of these 3 rules, and by reiterating what you know about the decimal numbering system, I'm kind of hoping that you'll be able to pick up these other numbering systems very quickly. So when it comes to the rules of counting, effectively the first rule refers to the base or the radix of the numbering system. And the base of the radix refers to the number of discrete levels that we have inside a numbering system. So when it comes to the decimal numbering system, we have a base or a radix of 10. We have 10 discrete levels. When it comes to a binary system, we have 2 discrete levels. When it comes to octal, we have 8 discrete levels. And of course, with hexadecimal, we have 16 discrete levels. So the first rule effectively defines the number of discrete levels that we have in the numbering system. And I will build upon this with the next 2 rules. Rule number 2 effectively means that when it comes to counting, when you start with the least significant level in the numbering system, which is generally in all of them 0, and you simply increment that number by 1 each time. When you reach the limit of the numbers inside that discrete, hit the limit of those numbers inside that numbering system, then effectively you have to reset that number back to the least digit, which in all these numbering systems is 0, and you need to increment the number that is to the left. Okay, so I'm slowly introducing that there's sort of a more than one number. There are numbers to the left. So when you exceed the number of digits in one column, you've then got to increment the digit to the left. So rule number 3 actually reiterates the column structure that we have with counting. We have the digits sitting inside columns. The column to the right is always the least significant digit. The column to the left is always the most significant digit. So generally when we're counting, we start with the least significant digit, increment that by 1. When we exceed the number of digits that we have in our numbering system, we reset that digit back to 0, and we increment the column immediately to the left. Okay? Those are the 3 rules of counting. So knowing those 3 rules, you can effectively apply them to any numbering system. So first of all, let's cover a numbering system that you're very much familiar with, the decimal numbering system. The decimal numbering system has a radix or base of 10, which effectively means that we have 10 fundamental digits or 10 discrete levels inside our numbering system. These discrete levels are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We can construct any decimal number using only these 10 digits. And each column inside our column-like structure that we have when we construct a number of multiple digits, each column increases by a power of 10. So our rightmost column starts at 1, is our ones column. The column immediately to its left is the tens column. The one next immediate to its left is the hundreds and the thousands, the 10,000s, the 100,000s, and so forth. So each column is a power of 10. So effectively, if you take the example down here where we've got 5374 written out of 4 decimal digits, effectively we start with the least significant digit, in this case is 4. This is 4 by 10 to the 0, which is 4, plus 7 by 10 to the 1, which is 70, plus 3 by 10 squared, which is 300, plus 5 by 10 cubed, which is 5,000. You add them all together, you get 5,000 plus 300 plus 70 plus 4, which is 5,374. When it comes to the decimal numbering system, there are 4 basic mathematical operations that we like to do with these numbering systems. These 4 basic operations are, of course, addition, subtraction, multiplication, and division. So when it comes to doing addition, we simply start with the least significant digit, or the least significant column in this case, which is the column where the 3 and the 9 are. We simply add those 2 digits together. 9 and 3 gives us 12. But hang on, 12's too big to fit in that column. We can't write 12 there. We've only got room in that column for 1 digit. So we simply leave the least significant digit there, the 2, and we move the 1, which in this case represents 10, to the tens column. So it appears in the tens column, and then we simply add up that column. So we get 1, 4, 3 gives us 8. So that is how we do our addition. We simply start with the least significant column, add those 2 together. Any overflow that we have in that column, we pass on to the next column. So if we get a number greater than 9 in the least significant digit column, then we pass the tens equivalent of that column into the tens column, and then we add up the tens column. Fairly simple stuff. When it comes to subtraction, we do the same thing here. We start with the least significant column. But hang on, if we've got to take the bottom line from the top line, we'll see that if we take 3 from 2, we're going to get a negative number. Okay, yes, we can handle a negative number, but it's not really going to make much sense. So what we do in this case, instead of when we did with addition, we carried to the left column. In this case, we want to borrow from the left column. So we simply borrow 1 from the left column to the left, the tens column, which makes the number on the top 12. And of course, because we borrowed 1 from the left column, we've got to normalise that out a bit. Because we've taken 10 from the left column, we've got to put a -1 in there to say we've taken 1 off. You can either put the -1 on the top, or you can add 1 to the bottom number. So you can either make the number on the bottom 4, or you can put a -1 up there. It depends on how you want to do it. So now that we've got our least significant column sorted out, we simply have 12. We take 3 from 12, which in this case gives us 9. And then we can simply deal with the next column. So this is going to be -1 from 8 is 7. And then we subtract 3 from 7, gives us 4. So that is the final answer, 49. So you can see in both these cases, whether it was addition or subtraction, we have started from the rightmost column, the least significant digit column, and we've slowly worked our way along to the left. So if these were 2 3-digit numbers, then we'd work on the hundreds column, and then the thousands columns, and so forth. So always work from the least significant digit, slowly making your way towards the most significant digit. Okay, so the next numbering system that we use in computers is in fact the binary numbering system. The binary numbering system has a radix of 2. So therefore we have only 2 fundamental digits. This is 0 and 1. The beauty of the binary numbering system is the fact that these 2 digits, 0 and 1, can be easily represented inside the electrical system of a computer. We can have circuits that are either on or off. If they're on, they represent 1. If they're off, they represent 0. We can also easily represent binary numbering systems inside memory cells. If a memory cell contains a charge, then it's considered a binary number of 1. If the memory cell doesn't contain a charge, then it's considered a binary equivalent of 0. So the binary numbering system is very well suited to the electrical nature of computers. The one thing that you need to take into account, though, is that when you represent a binary number, you're going to require a lot more digits than if you represented it using a decimal numbering system. For example, if we want to represent the number 127 in decimal, we require only 3 digits, 1, 2, and 7. If we try to represent the same number in in binary, then we're going to require 7 binary digits, which will be 1, 1, 1, 1, 1, 1, 1, 7 ones. So effectively, each column in our binary numbering system increases by a power of 2. Our least significant digit, like all our numbering systems, is always the ones column. So the rightmost column in this case will be the ones column. The column immediately to its left will be the twos column. The column immediately to its left will be the fours. The column immediately to its left will be 8, and so forth. Each time, each column multiplies or increases by a factor of 2, because 2 is our radix. The process of converting a number from binary into decimal is fairly straightforward. It's the same way that we converted a decimal number into a decimal number. We simply multiplied the number in that particular column by the column number raised to the radix. So the radix raised by that column number. So for this example here, we start with the least significant digit, which in this case is the 1. We simply go 1 times 2 to the 0, which of course this is 1 times 1, which gives us 1. We then multiply the next one, which is 0 by 2 to the 1, so 0 by 2, plus 0 by 2 to the 2, which is 4, so 0 by 4, plus 1 by 2 to the 3, which in this case is 8, plus 1 by 2 to the 4, which in this case is 16, plus 0 times 2 to the 5, which in this case is 32, plus 1 times 2 to the 6, which in this case is 64. So when you add them all up, so in this case, effectively we've got 64 plus 16 plus 8 plus 1, we get 89 decimal. When it comes to converting from decimal to binary, effectively what we do is we divide the number through by its radix. So what we do is we start with the number, we divide it through by the radix, which in this case is 2, so we go 145 divided by 2, gives us 72 with the remainder of 1. So we write down the 1. So we've got to keep track of not only the result of the division, the integer division, but also keep track of the remainders as well. So in this case we have 72 as the quotient and 1 as the remainder. So we keep track of both. Then we divide the quotient again, in this case 72 by 2, which gives us 36. And in this case we've got a remainder of 0 because 72 was an even number. Then we take 36, we divide it by 2, we get 18. Still we have a remainder of 0. We take 18, we divide it by 2, we get 9. Still a remainder of 0. We then take 9 and we divide it by 2, we get 4. In this case we have a remainder of 1 because 9 was an odd number. Then we take 4, we divide it by 2, we get 2, and we have a remainder of 0. We take 2, we divide it by 2, we get 1 with a remainder of 0. We then take 1, divide it by 2, we get 0, and a remainder of 1. Okay, at that point we stop. Okay, the point in which we stop is when the quotient, or in this case the result, is equal to 0. When we get our value to be equal to 0, that's when we stop. Okay, so when it's something equals 0, we stop. At that point, we now have our binary number encoded in the remainders. So if we start with the last remainder that we have, that is in fact the most significant digit of our binary number. Not the first remainder, the last remainder that we got is the most significant digit. So if you work from the bottom back up to the top, that is our binary number. Okay, so the very bottom line here, that remainder of 1 is our most significant digit. The very top line of this number where we got the remainder of 1, that is our least significant binary digit, and that is very important. You work from the bottom up. So that's how we reconstruct our binary number. So you can see our binary number in fact is 10010001. okay, where the MSB, to reiterate again, the most significant digit of our binary number is the last remainder, and the least significant digit of our binary number is the first remainder that we got. And then, of course, you can check that simply by doing the equation we did previously, where we can simply add all those numbers up, multiply by the radix in the column number, and we can see that we get exactly the same number again, 145. So that's how we convert our decimal numbers into binary numbers. Okay. Of course, when it comes to binary addition, it's the same thing when we had decimal addition. We start with the least significant digits. So in this case, it's 0 plus 0 gives us 0. In this case, it's 1 plus 1 gives us 2. Okay, but like before, we can't write 2 there because now we've tried to squeeze 2 digits into a column where it can only fit 1. So what we do is we leave the 0 there, and we move the 1 onto the next column. Okay, so now we go 1 plus 1 plus 1, which is 3. Same thing again, we can't fit those 2 digits there, so we leave the 1, and we move that 1 to the next column. So we have 1 plus 1, which is 1 plus 1 plus 0, which is 2. We write down the 0. We could then move that to the next column, but there is no next column, so we can just simply leave that there. So when we add binary numbers together, same way as when we did decimal, we start with the least significant column. We add the 2 together. If we get an overflow in that column, we pass the most significant digit of that overflow into the next column, and then we add up the next column. So we start with the least significant digit, and we slowly make our way to the most significant digit. Same thing when we do subtraction. It's the bottom subtracted from the top. If in fact we can't do that, we need to borrow from the column immediately to the left. Okay, in this case here, I've got an easier example where we don't actually have to borrow. So we've got 0 minus 0 gives us 0, 1 minus 1 gives us 0, 1 minus 1 gives us 0, and 1 minus 0 gives us 1. So that was a very simple subtraction. So had it been such a case where we had to borrow from the column to the left, then we'd simply add 1 onto the least significant column, so we'd make it 2 effectively, and then we would have to subtract 1 from the column next, which means either adding 1 to the bottom of it or subtracting 1 from the top. Okay, when it comes to octal numbering systems, effectively the number oct generally means 8, which defines that we have a radix or a base of 8. Therefore, we have 8 discrete steps, and therefore we have 8 fundamental units. So the 8 fundamental units we have in this case are 0, 1, 2, 3, 4, 5, 6, and 7. So they are our 8 fundamental digits. We can create any sort of octal number using only these 8 digits. Okay, so when we count with an octal number, we start at 0, like we do in any numbering system, and we simply increment. So we go 0, 1, 2, 3, 4, 5, 6, 7. And of course, the second rule of counting defined that when we exceed the number of fundamental digits, we reset that digit. So therefore we reset it back to 0, and therefore we increment the digit to the left, which means that the decimal number of 8 is in fact represented in octal as 10. So it looks like the number 10, but because it's octal, it's actually the number 8. Okay, so it can get quite confusing with these when you're mixing these numbering systems. So you need to clearly define what sort of base that you're using, whether you're using binary, decimal, octal, or hexadecimal, needs to be clearly defined. And we generally use subscript letters to define them. So in binary, it's usually a subscript B, hexadecimal is usually a subscript H, decimal is a subscript D, and octal is a subscript O. And stress that, subscript. Okay, so when it comes to conversion to decimal, you simply, like we did before, you take the columns of the number and you multiply them by the base or radix raised by the column number. And remembering that the rightmost column is in fact column 0 and the leftmost column is in fact the most significant, which depending on the number of digits could be column 1, column 2, column 3 or column 4, depending on the number of digits. So in this case here, with this number here, 1534, our leftmost column would in fact be column number 3. So what we do is we start with our least significant digit, which in this case is 4. We multiply that by our base, which is 8, raised to the power of 0. We then add that to the next digit, which in this case is 3, raised by our base of 8, raised to the power of 1, which of course in this case is 8. We then multiply this by 5, so add this to 5 by 8 squared, which then we also add 1 by 8 cubed. Okay, and when you add them all together, you get 860 decimals. So the important thing to note here is that you take each digit of this number and you multiply by its radix or base raised to the column number, and then we add them all together, and that will give us our decimal number. When it comes to converting a decimal number to octal, it is exactly the same story again that we had when we converted a decimal number to binary. We simply take the number and we divide it through by its base. In this case, our base is 8. So we take our decimal number, we divide it through by 8, we write down the result, or the quotient, and we keep note of its remainder. And then we take that result, which in that case was 18, we divide that through by 8, which gives us a result of 2, and a remainder of 2. We then take the result value and we divide that through by 8, which gives us 0. So at this point we stop. So same thing like when we had the binary, when we get a result of 0, that tells us to stop. And then we start with the last remainder, which in this case was 2, and that last remainder, as before, is our most significant digit of our octal number. So our octal number is in fact 221. So the last remainder is our most significant digit. The first remainder is our least significant digit. Okay, that's the very important thing to remember here, is that the last remainder is always the most significant digit. So our decimal number of 145 is in fact 221 in octal. Okay. Okay, so when it comes to converting a octal numbering system to and from binary, it's very easy, and that is because one of the natures of octal is the fact that our radix is 8. Okay, 8 is in fact a power of 2. Okay, because 8 is a power of 2, 8 is in fact 2 to the 3, which means that logically we can represent any octal number using 3 binary digits. So because our octal numbers are from 0 to 7, we know that using a binary number, a 3-digit binary number, we can represent any number between 0 and 7. Okay, so therefore when it comes to representing a octal number in binary, we simply take the octal number starting at the least significant digit. We take that least significant digit and we convert it into a 3-bit binary number. We then take the next octal digit and we convert that also into a 3-bit binary number. You then take the most significant octal digit and you convert that into a 3-bit binary number. And then what you do is you join those 3-bit binary numbers together to make one 9-bit number. And that 9-bit number is in fact the binary representation of a 3-digit octal number. So to give the example here, we've got 516 in octal, so that O on the end is not the 0, it's to define octal. Yes, it should be a subscript, but in this case it's pretty obvious it's not a 0. So we take those 3 digits and we split them up into their 3-bit binary equivalent numbers. So we start with 6, we split that up and we get 110 in binary, which is 6. We then go with 1, and that is 001 in binary. 5 is in fact 101 in binary, and then we join those 3-bit numbers together to make a 9-bit number, which is in fact our binary representation of that 3-digit octal. So 516 in octal is in fact 101001110 in binary. So the opposite also applies here. So when you try to convert from binary into octal, you simply take the binary number and you split it up into groups of 3. So we know that three binary digits can be used to represent an octal number. So we take each group of three binary digits, starting at the least significant binary digit. We segment that up into three, and then we convert that into an octal number. Take the next three, convert that into an octal, next three, convert that to octal, and so forth until we've run out of binary digits. So for example, we've got 1 0 1 0 0 1 1 1 0 in binary. So we split that up into 3-bit chunks. So we've got, starting from the least significant binary digit, we've got 0 1 1. So we know that's 6, so we write down the number 6. We then work on the next three. We've got 1 0 0. We know that's the decimal equivalent of 1. We then start with the last three binary digits, which is 1 0 1. And we know that's 5. So therefore we can join those 5 digits together to make our octal number, which in this case is 516 octal. Okay, the last the last important numbering system, I know I've got binary code decimal as well to talk about, but the last important numbering system is in fact the hexadecimal number system. So hexadecimal consists of a radix or base of 16. Okay, so we have 16 fundamental digits or 16 discrete levels in this numbering system. Because we only have digits in the decimal numbering system that go up to 9, we effectively use the first 6 letters of the alphabet to fill in the gap that's missing here. So when it comes to hexadecimal numbers, we effectively have 16 digits going from 0 to F. Okay, so A is in fact our equivalent of 10, B 11, C 12, D 13, E 14, and F 15. Okay, so you've got to keep that in mind. So we can make any hexadecimal number using these fundamental digits. So when it comes to conversion to decimal, we simply, like we've done before, we take each one of these digits and we multiply by its radix raised to the column number, and then we add them all together. So in this case, we start with the least significant digit, which is 1 by 16 to the 0. We then add that to 8 by 16 raised to the power of 1. We then add that to C, which in this case is 12, 12 by 16 squared. We then add that to F, which is 15, so we're going to translate these letters into their decimal equivalents before we multiply them. So we've got 15 times 16 cubed. So then once we've multiplied them all out and we've added them all up, we'll in fact get 64,641 in decimal. Okay, it's pretty obvious that using hexadecimal digits, we can in fact use less digits to represent a decimal number. So we've only used 4 hexadecimal digits here, FC81, to represent a 5-digit decimal number, which is 64,641 decimal. So we need less digits to represent a hexadecimal number. That's because the radix of a hexadecimal number is greater than the radix of a decimal number. So when we're converting from decimal to hexadecimal, then it's the same thing we've done before, and this is the whole thing of why I've done it this way, is the repetition. We repeat and repeat and repeat, and hopefully, it might be boring as all hell, but hopefully it becomes very clear on how we convert from one numbering system to another, irrelevant of what that numbering systems are. So when it comes to converting from decimal to hexadecimal, we effectively just take that decimal number and we divide it through by its radix. In this case, the radix is 16. So we take our number, divide it through by 16, we'll get some sort of result. Okay, so 64,641 divided by 16 gave us 4,040 with a remainder of 1. Okay, so we keep track of those two numbers. Then we take that result or quotient again and we divide it through by 16 again. So 4,040 divided by 16 gives us 252. Remainder in this case is 8. So we take 252, we divide it through by 16, we get 15 with a remainder of 12, which we convert to be C. We then take 15 divided by 16, we get 0. So that's our ending point yet again. So each of these times when we hit 0, we stop. And then of course in this case the remainder is 15, or convert it to the hexadecimal equivalent, which is F. So therefore, starting at the last remainder that we got, that is our most significant digit. So the last remainder of 15 is our most significant. The first remainder of 1 is our least significant digit of our hexadecimal number. So we can simply take those remainders and piece our number back together, which in this case is FC81 hexadecimal. Okay, so like we had with octal, when it comes to hexadecimal numbering systems, we have a radix of 16. So like octal, which had a radix of 8, 16 is also a power of 2. So with octal, it was a radix of 8, which was 3 binary digits. So with hexadecimal, we have a radix of 16, which is in fact 4 binary digits. So 2 to the 4 is 16, so therefore using 4 binary digits we can represent any hexadecimal digit. So therefore it's just a matter of taking the hexadecimal number and splitting it into chunks of 4 bits. So starting with the least significant digit of the hexadecimal number, we get 1, and we generate from that 1 a 4-bit number, okay, so which of course is 0001. We then take the next digit, which in this case was 8 from a hexadecimal number, and we convert that into a 4-bit number, which in this case is 1000. We then take the next digit, which is C, and we convert that into a 4-bit binary number, which in this case is 1100. So that's our C. We then take our F and we convert that, or in this case 15, convert that into our 4-bit binary number, which in this case is 1111, and then we take all those numbers and we just simply join them all together to make one big giant 16-bit number. So, of course, the opposite also applies. When we go to convert from binary back to hexadecimal, we simply take the binary number, starting at the least significant digit of the binary number, and we split them up into chunks of 4 bits. And therefore, using each of the 4 bits, we then convert them to the equivalent hexadecimal number. So in this case here, we've got 1011001011000101 in binary, and we want to convert that into hexadecimal, so we break them up into chunks of 4. So starting at the least significant digit, we get 0101. We join them up, we can convert that into a decimal, that gives us 5. Take the next one, which is 1100. That's 8 plus 4, which is 12. Now that's C in hexadecimal. Take the next one, which is then 0010. We know that's 2, so write down 2. And then we take the last one, which is 1011, which is 11. And we know that 11 is B in hexadecimal. So therefore the number is B2C5 hexadecimal. Okay, when it comes to binary coded decimal, I'm not going to speak too much about this because it's pretty much a dying numbering system. It's still used in some input-output situations, and effectively during one of the labs you will in fact use a binary coded decimal display. But when it comes to binary coded decimal, it's not a huge jump from the numbering systems we've talked about before. With binary coded decimals, effectively we use 4-bit numbers to represent the decimal digits. Obviously we can't use 3-bit numbers because using a 3-bit number we can only represent 0 to 7. So using a 4-bit number we can represent the numbers from 0 to 9. Obviously with a 4-bit number we can in fact represent numbers between 0 and 15. So there are some invalid numbers, so to speak, inside a binary coded decimal. So we can only use the 4 bits to represent numbers between 0 and 9. And there are a lot of mathematical instructions on the processors these days that allow to compensate for overflows. So if you do add 2 binary coded decimal numbers together and you get a number that's say 11 in those 4 bits, then effectively the instructions will compensate for it and fix out the binary coded decimal number for you so that it's a proper representation of binary coded decimal. But the instructions are available there. So using an 8-bit number, we effectively can represent any number between 0 and 99, as opposed to if we use it as a standard binary number, we can represent any number between 0 and 255. So binary coded decimal, each 4-bit is effectively represents a decimal digit. Okay, so one of the last things that we're going to talk about is, of course, when it comes to representing negative numbers on a processor. Okay, up until now we've talked about positive numbers, but how do we represent negative numbers? When I talk about negative numbers, I'm going to talk about three numbering systems and illustrate the problems with those numbering systems. So we'll talk about signed modulus or signed bit extension. We'll talk about ones complement method and of course the twos complement method. So these three numbering systems are used on microprocessors these days. They have their advantages, they have the disadvantages, and I will illustrate them to you over the next few slides. So when it comes to signed modulus, effectively the most significant bit represents the sign bit. So if it's a 0 in the most significant bit, then it's considered positive. If there's a 1 in the most significant bit, then it's considered negative. So it's the most significant bit of the number that effectively defines the sign of the number. So that's why it's called signed modulus. However, there are some problems with using signed modulus. With signed modulus, effectively we have two zeros. We have a 0, 0, 0, 0, and of course we have 1 with all zeros. So we have a plus or minus 0. Okay, that is the first problem we have. So we're actually not effectively using our bits. We've like wasted a whole, I guess, one whole bit combination on having two zeros. Okay, that's the first problem. We have two zeros. Okay, the second problem is that there's no additive inverse. We can't simply go use a signed modulus, make a negative number, then add the two together and get 0. It doesn't work that way. So if we take 34 and we add negative 34 to it, you'd expect to get 0. But however, if you take 34 and you make negative 34, you in fact get negative 68. So effectively you've just simply got it adding the two numbers together and then transferring the sign bit. So it's not really a true additive inverse. In order for this to work properly, you'd have to have a considerable amount of additional logic to basically ensure that this didn't happen. So with signed modulus, there is no easy additive inverse. With the ones complement, when it comes to calculating a ones complement, we simply take the number and we simply negate the 8-bit. So we simply take an 8-bit number of 37, so we simply write it down as 37 and we simply toggle each bit, okay, or invert it, and therefore we get a negative number, which is simply an a binary inversion of the original number. So effectively we have a negative 37D. Okay. However, we still have those two problems we had before. We still have the negative, we still have two zeros, and we don't have a negative inverse. However, if we take that ones complement one step further and we use it to create a twos complement number, then we can hopefully overcome all these problems. So the most common way that we use to represent negative numbers on a microprocessor these days is using twos complement. So what we do is we take a binary number, we simply take the decimal number, we convert it to its binary equivalent, we then negate or invert all the bits, so we do a ones complement on it. Okay, that's obviously going to cause other issues, but we're not going to stop there. Then the last thing we do is we simply add 1 onto it. Okay, so if you take the number 37, convert it to its binary number of 001000101, we then invert all those bits, so we get 1101, 1010, and then we add 1 to it, then we'll get the negative 37 twos complement equivalent, which in this case is 11011011B. However, all our problems are now solved. If you look at the numbers in the blue table there, you'll see that we in fact only have one representation of 0, which of course is what we'd expect, 0. There is no 100 because that's in fact negative 4 in a 3-bit numbering system. Okay, so we have only 10. The next thing is we all of a sudden miraculously have an additive inverse as well. Well, if we take one key assumption into account, we effectively have an additive inverse. If you take a positive number, so if you take 3 and you add it to the negative 3 equivalent, so you get 1 and 1 is 0, which carries the 1, you get 1, 1 is 0, carries the 1, you get 1 and 1 is 0, carries the 1, we effectively get 1, 0, 0, 0. Okay, so that's not really an additive inverse, but if you take into account the fact that if we had a 3-bit processor, the processor itself would only have 3 bits to store that result, which means that 1 there in brackets would effectively disappear. We don't have the space to hold it, we lose it. So effectively, as long as we have numbers to the size of our registers, or size that our processor can deal with, when you add a number to its inverse, you'll effectively get a 0, but a 1 bit will fall off the end and disappear into oblivion. So effectively it will give you an additive inverse. So using 2's complement fixes all our problems. Okay, so now we've talked up till now about how we can represent different numbering systems, how we can represent negative numbers, but how do we go about representing big numbers? Okay, let's say we've only got registers in our processor that can hold 8-bit numbers. How do we enable it to, say, deal with 16-bit numbers or 32-bit numbers or numbers that are bigger than what we can handle? This is where we can start using multi-word numbers. So microprocessors generally have a fixed word size. They're either 8-bit, 16-bit or 32-bit processors, and that generally defines the internal bus, which also impacts on the internal register sizes that we have in our processor. So we have a limited range of numbers that we can represent with these registers. So how do we represent bigger numbers? Well, that's where we do multi-word numbers. So with an 8-bit microprocessor, generally you have an 8-bit word length. We can represent numbers between 0 and 255. How could it represent a larger decimal number, so such as 3,867, okay, which consists of more than 8 bits? Okay, what we can do is we can actually split the number up into 2 8-bit numbers. So we take that 16-bit number and we split it up into 2 8-bit components, and we label those 8-bit numbers as either the most significant byte and least significant byte. Okay, so therefore we can see which 8 bits are the least significant digits, which the 8 bits are the most significant. So it's least significant byte, most significant byte. Okay, and we put them in 2 locations. Location number 1 for the MSB, location number 2 for the LSB. Okay, so when we deal with multi-word numbers, you've got to take some things into account. Okay, we've got to be very careful. You've got to deal with the LSB first and then the MSB. So if you take a 16-bit number and you add it up, effectively you start with the least significant digit first. So you do the least significant digit, you add them up, making your way very slowly to the most significant digit. Same thing happens when you deal with multi-word numbers. You first of all start with the least significant digit, which is in the least significant byte. So you simply add them up, starting from the least significant digit all the way up to the most significant digit of the least significant byte. When you hit that most significant digit of the least significant byte, if you get an overflow, okay, you've got to keep track of that overflow. So generally we'll have a mechanism inside the processor to keep track of that overflow. So in this case here, we're not going to lose that one. It's not going to fall over and disappear and go into oblivion. We're going to keep track of it, okay, which usually we'll put it inside a carry bit. So then what we do is we keep track of that 1 bit, and then when we add up the most significant bytes, we take into account and we bring in that the carry bit, so to speak, and we add that on to the most significant bytes. So then simply we add it up, passing on the carry bit to the least significant digit of the most significant byte, and we simply add it up as normal. And then what we do is we then, with the most significant byte on the front, least significant byte on the end, we effectively got our 16-bit number, and you can see the numbers are exactly the same. Just got to be careful on how we deal with them. Okay. When it comes to representing multi-word numbers, there are 2 main ways of doing it. One is we can store them in little endian mode or big endian mode, and this depends on how we store them in memory. Okay, when it comes to storing with big endian, we effectively put the most significant byte in memory, and then we put the least significant byte immediately following it inside memory. When it comes to little endian, we put the least significant byte first, and then following it in memory, we then have the most significant byte. One thing you've got to keep in mind is that big endian representation works very well in 16-bit processors because you can do a 16-bit read straight from memory, give it the least significant, give it the smaller address, and then it will read the 16-bit number from that address, which means it will read the most significant byte and then read the least significant byte from the immediately following address. So it will simply do a 16-bit read. The S12X, or the ADAPT9 S12 that we'll be using in labs, is based on the big endian representation. When it comes to little endian representation, this is what Intel processors are based on. This is where we store the least significant byte first and then the most significant byte, which generally requires that if you're going to do a 16-bit read out of memory, the processor effectively has to swap those bytes when it reads them in automatically. This is a problem as a result of historical requirements. So when they eventually had 8-bit processors, when you've got an 8-bit processor, you need to deal with the least significant byte first, as shown by the previous example, and then once you've dealt with that, then you need to read in the most significant byte and then add the carry on to that and so forth. So when it comes to 8-bit processors, you want the least significant byte first, then the most significant byte, and so forth. So obviously when they moved to 16-bit processors, they had to do that automatic swapping internally because there were still 8-bit PCs out there, and when they brought 16-bit in, the software still has to work on both, so the processors had to internally swap them. So it's a bit of a historical problem, I guess. So with the HS12X, or the ADAPT9 S12X that we're using in labs, we're using big endian. Okay, so it's MSB, then LSB. Okay, should you require any further assistance on this lecture topic, then please do not hesitate to ask your demonstrator. They are there to help you. Don't hesitate in posting a question on the forum. Okay, so the forum's there to help. Put some questions on there and get some feedback from me and your colleagues and your peers. You can email me. Okay, I'm very quick to respond to emails, or you can make an appointment to see me, or grab me after the lecture, grab me after tutorial, whatever's easiest for you, but please ensure that all your questions get answered.